The effect of climate change on temperature and precipitation in Seattle, Washington. Over half of Washington state's population lives west of the Cascade Mountains. Seattle is a bustling city with the highest population of residents of all cities in Washington state. As of 2017, Seattle had a population of 724,745. Seattle is home to famous locations such as the Space Needle, Pike Place Market, and Seattle Waterfront. Western Washington exports important goods such as aircraft parts, soybeans, wheat, corn, petroleum, coniferous wood, potatoes, and apples. The climate of Western Washington affects the city of Seattle's productivity and livelihood. A changing climate lends itself to a changing city that climate science and meteorology can help us prepare for. The weather of Western Washington is influenced greatly by its topography and proximity to the marine environment. Its unique climate is important to the lifestyles of over 700,000 people living in the city of Seattle alone. The objective of our research is to identify climate change in Seattle by measuring change in temperature and precipitation from the past, present, and future. We hypothesize that global warming is expected to affect climate drivers for Seattle, producing an increase in temperature and precipitation over time. We will analyze data from the years 1981 to 2010 to understand climate trends of Seattle's past, 2014 to 2019 to understand Seattle's current climate, and climate change projections to attempt to grasp the future Seattle faces. We based our thesis on the analysis of 3 climate drivers for Western Washington. The atmospheric processes we identified to drive climate for Seattle include orographic uplift, Aleutian low, and land-ocean thermal contrast. We hypothesize an increase in precipitation in Seattle over time due to increased sea surface temperatures. We expect increased sea surface temperatures in the northern Pacific to lead to increased evaporation, causing more water vapor to be carried, condensed, and eventually released as precipitation during orographic uplift at the Cascade Mountain Range. As the humid ocean air begins to climb the steep Cascades, the air mass begins to cool and water vapor begins to condense and eventually precipitate. In Western Washington, this precipitation often falls as snow in the winter months. The precipitation brought on by orographic uplift west of the Cascade Mountains would bring precipitation to the land area west of the mountains in which Seattle resides. The Pacific Northwest rain shadow immediately affects areas on the western slopes of the Cascades. Seattle is not located directly on the Cascade slopes. However, the concept of orographic uplift is important to understanding that the weather of Seattle is not protected by these large mountains. Although Seattle is not located on the mountain slope, the city still resides on the windward side of the mountains. We have chosen to highlight the orographic effects of the Cascades rather than the Olympic mountain range because many peaks of the Cascade Range exceed 10,000 feet, while the highest peak of the Olympic range is Mount Olympus at 7,965 feet. In the scope of our research, the orographic effect of the Cascade Mountains, known as the Pacific Northwest Rain Shadow, is of greater effect. Considering the idea of orographic uplift, we propose an overall increase in precipitation for the Seattle area over the time period of 1981 into the future. The effects of the Aleutian low have also been taken into consideration when creating our hypothesis. We assert that global warming will cause a strengthening of the Aleutian low, leading to increased precipitation in western Washington. The Aleutian low is a low-pressure area located in the northern Pacific, specifically over the Gulf of Alaska near the Aleutian Islands. It is a semi-permanent, low-pressure area from which storms often begin or gain power. The Aleutian low gains its maximum intensity during winter months, generating often unfavorable winds and waves. The low deteriorates in the summer, sometimes completely losing all strength and disappearing. The Pacific High is another regional pressure system that must be considered when analyzing the climate of western Washington. In the warmer summer months, a high-pressure system located off of the coast of California supplies relatively dry weather to the western United States due to its counterclockwise rotation of air. In the summer months, the Pacific High reaches the northern extent of its range, creating more of an effect on Washington than in the winter months, when the high-pressure system makes its way to the south. This southward seasonal migration of the Pacific High allows for the movement of wind and polar fronts towards western Washington and Seattle during the winter, while its northward migration in summer helps create fair weather days for this west coast region. As increased temperature is known for the speeding of reactions and promoting of extreme weather, we hypothesize that the increase in global temperature brought on by global warming will strengthen the Aleutian low, sending unpleasant winter weather and increased precipitation to Seattle. The strengthening of the Aleutian low would bring increased precipitation to western Washington, including Seattle, during the winter months. As global temperatures increase due to global warming, we hypothesize that the land-ocean thermal contrast will continue creating precipitation in western Washington, and precipitation will be strengthened by increased evaporation over the ocean. As sea surface temperatures rise, we expect an increase in the amount of evaporation taking place over the northern Pacific. Climate change is expected to continue to increase the temperature of both land and ocean. Therefore, we do not predict the land-ocean thermal contrast to strengthen, but we do hypothesize an increase in precipitation resulting from an increase in sea surface temperature, resulting in higher levels of evaporation. The land-ocean thermal contrast is responsible for the coastal climate that Seattle and western Washington experience. Land is more heavily affected by the sun's daily warming, while ocean temperatures stay relatively stable. The interaction between the two different air masses, one formed over land and one formed over ocean, result in the characteristic coastal climate found in Seattle. The differences in temperatures cause convection currents, resulting in ocean breezes, and we hypothesize with an increase in water vapor, there will be increased precipitation. After taking into consideration the effects of orographic uplift, the Aleutian low, and the land-based thermal contrast, we hypothesize global warming will cause an increase in temperature and precipitation over time.
To understand climate change trends in Seattle, we must first take steps to understand the weather and climate of the past. James E. Whitworth recorded the first weather observation in Seattle on February 16, 1870. Whitworth recorded the temperature as 55 degrees Fahrenheit under clear skies and calm wind. The original report was sent to the Smithsonian Institution. The weather observation taken at 2 p.m. marked the beginning of a long history of weather observation for the Seattle area. The responsibility of weather observation has switched hands multiple times in the past 149 years. From the Smithsonian rose the U.S. Army's Signal Service observers, followed by the formation of the Weather Bureau. Today, we turn to the National Weather Service for weather observation and forecasting. A measurable effect of climate change in western Washington is reduced snowpack. The spring snowpack measures of the Cascade Mountains have been decreasing over time. This decrease in snowpack is attributed to rising global temperatures. In the 77-year span from 1930 to 2007, spring snowpack decreased by 23%. This is significant because it was in the time period where global warming increased most rapidly. While during the 31-year span period of 1976 to 2007, snowpack increased by 19%. The increase is statistically insignificant because of annual variability. The U.S. Department of Energy predicts that an impending decline in snow cover of the Cascade Mountain Range will cause a 70% decrease in the amount of water provided by the mountain snow. Declining glacier size and snowpack levels are being recognized as global phenomena plaguing mountain ranges worldwide. For our analysis of temperature and precipitation, we will be using data provided by NOAA and the National Weather Service from 1980 to 2010. The data used in our analysis of Seattle's climate from 1981 to 2010 is provided by NOAA. The data can be found on NOAA's Climate Data webpage, available for public access and interpretation. The charts created by NOAA display monthly averages for the years 1981 through 2010 for Seattle-Tacoma International Airport. An average has been computed for each month through the years. For example, the average temperature displayed for the month of January was calculated by taking the average temperature of every January from 1981 to 2010. From the chart, our focus will be on the blue line, which represents precipitation, and the orange line representing temperature. Charts display precipitation from 1981 to 2010 as highest in the winter months. Taking a closer look at the chart provided by NOAA, November was found to have the highest average monthly precipitation with an average of 6.57 inches of rain each November from 1981 to 2010. January comes close second with an average precipitation of 5.57 inches, and December had an average of 5.35 inches. July was found to have the lowest average monthly precipitation with an average of 0.70 inches of rain each July from 1981 to 2010. August had an average precipitation of 0.88 inches, falling close behind the footsteps of July. The highest monthly average temperature is reported to be in August, with an average monthly temperature of 66.1 degrees Fahrenheit. The lowest monthly average temperature is reported in December at a chilly 40.6 degrees Fahrenheit. The average annual range of temperatures is 25.5 degrees Fahrenheit. Now let's examine the current climate of Seattle. When it comes to weather, Seattle is a mild city. Temperatures stay relatively mild year-round, between 40 degrees in the winter daytime and 80 degrees in the summer daytime. Annual average precipitation is around 37 inches. There are plenty of gray days, but summer days are the driest. Winter is typically rainier. Although Seattle is known for gray skies, Fort Lauderdale, as part of sunny South Florida, receives on average about 67 inches of precipitation a year, while Seattle receives astonishingly less at 37 inches. Seattle's topography, proximity to the sea, and latitude produce a unique climatic environment. The data used for the analysis of the present climate of Seattle is provided by NOAA National Weather Service Forecast Office, Seattle, Washington. Under Observed Weather Reports, preliminary monthly climate data for the years 2014 through 2019 was found. Preliminary monthly data reports include daily weather statistics for the month, such as temperature, precipitation, degree days, wind, and sky cover. The location chosen was Seattle-Tacoma Station. the same location used for the data collected for the years 1980 through 2010. For the data from 2014 through 2019, through simple mathematical computations, monthly averages for temperature and precipitation were created from the original NOAA raw data. The NOAA National Weather Service data gave the total precipitation and average temperature for each month from April 2014 to April 2019. From this data, we calculated the average monthly precipitation and average monthly temperature. For example, the average monthly temperature for May from the years 2014 through 2019 was calculated by adding all of the monthly averages for the 5-year period and dividing by the number of years for which data was found. Precipitation data from NOAA was only available in total precipitation by month. Total precipitation was divided by the number of days in that month. Then these numbers were added for all of the same months. Finally, the total was divided by the number of months for which data was found. November was found to have the highest average monthly precipitation, with an average of 6.7 inches of rain each November from 2014 through 2019, followed most closely by December with an average of 6.2 inches. July was found to have the lowest average monthly precipitation, with an average of 0.3 inches of rain each July from 2014 through 2019. June had an average precipitation of 0.9 inches, following most closely behind the footsteps of July. The highest monthly average temperature is reported to be in August, with an average monthly temperature of 69.1 degrees Fahrenheit. The lowest monthly average temperature is reported in December at a chilly 42.2 degrees Fahrenheit. The average annual range of temperature is 26.9 degrees Fahrenheit. We will use data from the present, 2014 to 2019, to compare the data from the past, 1980 to 2010, to attempt to realize trends in precipitation and temperature. Through comparison, the hypotheses of increased precipitation and temperature will be evaluated.
Now for research of future climate. Climate projections for Seattle used in this presentation were acquired through several resources, including an article from the journal Climate Change, published in 2010, titled Implications of 21st Century Climate Change for the Hydrology of Washington State. The lead scientist, M.M. Elsner, is a climate scientist from the University of Washington. We also utilized Washington State's Integrated Climate Response Strategy, published in April of 2012. In addition, an article titled On the Response of the Aleutian Low to Greenhouse Warming, published in 2017 by the American Meteorological Society, was also used, as well as the webpage Climate Impacts in the Northwest from the Environmental Protection Agency. The information from these resources were reviewed, resulting in the following conclusions regarding temperature and precipitation. By reviewing the documents, the following information was gathered regarding future change in temperature for Seattle. The research led by M.M. Elsner asserts that there will be 0.5 degrees Fahrenheit of warming per decade, while the report from the state of Washington states temperature will increase by 2 degrees by 2020, 3.2 degrees by 2040, and 5.3 degrees by 2080. While projections from the EPA explain there will be a warming of 3 degrees Fahrenheit to 10 degrees Fahrenheit by 2100. From this information, we conclude that the temperature in Seattle is expected to rise with time. By reviewing the same documents, the following statements about the future of Seattle regarding precipitation were found. According to Elsner in 2010, there will be 0.2 to to 1.9% increase in precipitation by 2020, 2.1 to 2.2% increase in precipitation by 2040, while the projections for longer timeframes are much more variable. The projections by Elsner for 2080 range from a decrease in precipitation of 10% to an increase of 21%. However, it is explained that increased winter precipitation and decreased summer precipitation is expected. Examining the integrated climate response strategy from the state of Washington, it becomes clear different models project different changes in precipitation. With moderate greenhouse emission scenarios, an 8% increase in winter precipitation is expected by 2080. Some models show up to a 42% increase in winter precipitation, while the average estimation of decrease in summer precipitation is 14%. Other models show a range of 20 to 40% decrease in summer precipitation. Some models deviate even further from these statements and project dry winters. The models attribute dry winters to rising temperatures resulting in decreased precipitation. The State of Washington report also asserts that climate change will mean more intense extreme weather events for Seattle. Models show the magnitude of large storms for Seattle will increase 14 to 28% by 2060. This percent increase refers to the intensity of storms, not the number of events. When looking at the precipitation projections published by the EPA webpage Climate Change Impacts, increased rain and decreased snow are projected due to warming temperatures caused by global warming. Summer precipitation is projected to decline by as much as 30%, with less frequent but heavier downpours. The EPA states changes in average annual precipitation in the Northwest is likely to vary over the course of the century. During our research, information was gathered on the impacts of climate change on the Aleutian Low and the land-ocean thermal contrast. According to the 2017 article from the American Meteorological Society on the response of the Aleutian Low to greenhouse warming, the Aleutian Low is expected to strengthen and become larger, spreading further north. The strengthening of the low depends largely on the sea surface temperature of the tropical Pacific as well as the warming of the Asian continent. The Aleutian Low brings wet winter weather to the northwest, and its strengthening could mean wetter winters for Seattle. The article also asserts that a warming climate could lead to a weakened land-ocean thermal contrast, which in turn can cause a weakened Aleutian Low. However, by most models, the Aleutian Low is expected to be strengthened, overcoming the effects of the weakened land-ocean thermal contrast. Keep in mind for all of these predictions, reviewed to evaluate future climate scenarios, atmospheric processes are difficult to model and predict. Seasonal variation often occurs, affecting temperature, precipitation, the Aleutian Low, and land-ocean thermal contrast. Atmospheric processes are complicated systems. In the Pacific Northwest, the effects of the El Niño Southern Oscillation and the Pacific Decadal Oscillation, as well as variations in other phenomena, can cause deviation between expected climate forecasts and reality. We hypothesized that global warming was expected to affect climate drivers for Seattle, producing an increase in temperature and precipitation over time. The first part of our hypothesis states that temperature will increase in Seattle over time. We will compare the results of past, present, and future temperature information we have gathered to accept or reject our hypothesis of increased temperature. By comparing data utilized to understand the past with data utilized to understand the present, the research hopes to identify any trends in temperature and precipitation changes. The table was created to compare data from 1980 to 2010, the past, to data from 2014 to 2019, the present. For changes in average temperature, red color signifies an increase in temperature, while the blue color signifies a decrease in temperature in degrees Fahrenheit. The change in degrees Fahrenheit is exhibited in the far right column. In the temperature table constructed, the trend of increasing temperature is easy to identify. The average temperatures for each month increased from the 1980 to 2010 data to the 2014 to 2019 data. The largest increase in average monthly temperature was found for the month of May, with an increase in average temperature of 3.4 degrees Fahrenheit from the past and present data sets. February was the only month where the average monthly temperatures from 1980 to 2010 was higher than the average monthly temperatures from 2014 to 2019. The monthly average temperature decreased by 0.3 degrees Fahrenheit between the 1980 to 2010 and the 2014 to 2019 dataset. All sources used for the prediction of future climate state that temperature for Seattle is expected to increase. However, variability occurs in the rate of increase. Therefore, we conclude that temperature in Seattle is increasing over time, accepting this aspect of our hypothesis. The second part of our hypothesis states that precipitation will also increase over time in Seattle. By analyzing the monthly averages of precipitation for the 1980 to 2010 dataset and the 2014 to 2019 dataset, and comparing the averages, a clear trend is harder to establish. Under changes in average precipitation, the dark blue color signifies an increase in precipitation, while the light blue signifies a decrease in precipitation. The exact difference can be seen in the column furthest to the right. The data for precipitation is in inches. For 7 out of 12 months, the amount of precipitation increased. February, March, April, August, October, November, and December all experienced an increase in precipitation averages from the 1980 to 2010 dataset to the 2014 to 2019 dataset. The largest increase was in October, where a 2.56-inch gain was realized between the past and present averages. For the remaining 6 months, January, May, June, July, and September, precipitation averages between past and present decreased. The largest decrease in precipitation averages occurred in the month of June. 0.6 inches of precipitation were lost between the averages of the past and present datasets. For future projection of precipitation, results were just as variable. Some sources projected increased precipitation. Others projected decreased precipitation. Some sources projected drier summers and wetter winters, while some projected drier summers and drier winters. However, changes in the type of precipitation are expected to occur. There will most likely be a higher percentage of precipitation falling as rain and less percentage of precipitation falling as snow due to warming air temperature. Our research results for precipitation amount are inconclusive, and therefore we cannot accept our hypothesis that precipitation in Seattle will increase over time. Our hypothesis states that global warming will affect climate drivers. However, the effect of rising temperature on orographic uplift, the Aleutian low, and the land-ocean thermal contrast for western Washington is difficult to assess. Future projections vary on the effect of greenhouse warming on the Aleutian low, although the overall conclusion is that it will strengthen and the land-ocean thermal contrast is expected to weaken. The degree to which each process will be affected by global warming is beyond our scope of research. The research presented could be built upon and improved. For data to represent the past, monthly averages were used from NOAA for the years 1980 to 2010, while for data to represent the present, monthly averages were calculated using data for each month of each year from 2014 to 2019. Data was not included from the 3-year spread of 2011 to 2013. NOAA data was not found for the period of time from 2011 to 2013, jeopardizing the accuracy of our results. NOAA National Weather Service preliminary monthly data is only available for the past 5 years from the current month. The comparison of averages from 1980 to 2010 with averages from 2014 to 2019 was deemed acceptable for our scope of research with limited available data. 2 separate time periods were needed for comparison, and the comparison of averages from these time periods provide an acceptable analysis of the change that occurred over 39 years. Our inability to go further back in time also challenges the validity of our conclusions. For more accurate analysis of Western Washington's changing climate, research should be done to compare paleoclimate data to climate data of the past few hundred or thousand years. Because of our small timescale, climate change trends are not easily seen as they are in larger geologic timescales. Instead, our data is more affected by seasonal variations, including the El Niño Southern Oscillation, the Pacific Decadal Oscillation, and changes in solar radiation intensity. Our small scope of time does not fully enable our research to be used as long-term climate change analysis, but rather analysis of climate change that can be seen in one modern lifetime.
In conclusion, we have found that temperatures in Seattle will continue to increase in time as it has from the 1980s to today. We did not find conclusive data about the amount of precipitation expected in Seattle for the future, nor were we able to identify trends in the precipitation amount from 1980 to today. For these reasons, our hypothesis that temperature and precipitation will increase due to the effect of global warming on climate drivers cannot be accepted. Further research should be conducted to understand the effect of global warming on the climate of Western Washington.